Examination, Chemistry Optional, Paper I, Section B, features Chemistry of F block elements as a highly structured, scoring, and recurring topic. Questions typically target periodic trends, oxidation states, magnetic properties, and separation techniques of lanthanides and actinides. The following selected high-yield questions from past UPSC papers are organized by subtopic, complete with model answers written in the standard format expected by examiners. 1. Lanthanide contraction and its consequences. Question 1. A. What is lanthanide contraction? Explain its fundamental cause. B. Discuss two major consequences of lanthanide contraction on the post-lanthanide elements, 5D transition series. Model answer. A. Definition and cause. Lanthanide contraction refers to the steady, regular decrease in the atomic and ionic radii of lanthanide elements, M-3+ icons, with the increase in atomic number from lanthanum, Z equals 57, to lutetium, Z equals 71. Cause. As we move along the series, the nuclear charge increases by 1 unit at each step. The incoming electron enters the inner 4f subshell. The shape of 4f orbitals is highly diffused, leading to extremely poor shielding of one 4f electron by another. Consequently, the effective nuclear charge, Z_EFF, experienced by the outermost electrons increases steadily, pulling the electron cloud closer to the nucleus and causing a size contraction. B. Consequences. Similarity in the size of 4D and 5D elements. Due to the intervening lanthanide contraction, the expected size increase from the 4D to the 5D transition series is neutralized. Pairs of elements like Zr, 4D, and HF, 5D, or Nb and Ta, possess almost identical ionic and atomic radii. Difficulty in separation. Because Zr and HF have identical sizes and similar chemical properties, they always occur together in nature, and separating them cleanly is extremely difficult. Basicity difference. The basic strength of lanthanide hydroxides, MO_3, decreases from La_O_3, most basic, to Lu_O_3, least basic. As the size decreases from La_3+ to Lu_3+, the covalent character of the MO bond increases, Fujans rules, making it harder to release O icons. 2. Oxidation states and stability. Question 2. Although +3 is the principal oxidation state for lanthanides, cerium shows +4 while europium and ytterbium exhibit +2 oxidation states. Justify this behavior on the basis of electronic configuration. Model answer. The general electronic configuration of lanthanides is X, 4F 1 to 14, 5D 0 to 1, 6 squared. The most stable oxidation state across the series is +3 because the sum of the first three ionization enthalpies is highly compensated by the hydration or lattice energy. However, anomalous +2 and +4 oxidation states arise primarily from the extra thermodynamic stability associated with empty, F-0, half-filled, F-7, or completely filled, F-14, subshells, cerium, Ce, Z equals 58. Electronic configuration is X, 4F 1 5D 1 6 squared. By losing 4 electrons, it forms Ce 4+, with a stable X, 4F empty F orbital configuration. Hence, Ce 4+ acts as a strong oxidizing agent, readily converting back to the stable Ce 3+ state. Europium, EU, Z equals 63, electronic configuration is X, 4F 76 squared. By losing 2 electrons from the 6 orbital, it forms U 2+, retaining a highly stable, symmetric half-filled X, 4F 7 configuration. Ytterbium, YUB, Z equals 70, electronic configuration is X, 4F 14, 6 squared. Losing 2 electrons yields YUB 2+, which maintains a stable completely filled X, 4F 14 configuration. 3. Magnetic and spectral properties. Question 3. Explain why the electronic absorption spectra of lanthanide complexes consist of very sharp, line-like bands, whereas D-block transition metal complexes exhibit broad bands. Model answer. The stark difference in the absorption profiles of F-block and D-block complexes is rooted in the spatial orientation of their valence-valence orbitals, feature. Lanthanide icons, F-block, transition metal icons, D-block, orbital shielding. The 4F orbitals are deeply buried within the atom, shielded from the external environment by the filled 5 squared and 5p 6 subshells. The outermost 3D, or 4D, 5D, orbitals are exposed directly to the external chemical environment. Ligand interaction. The surrounding ligands, solvent molecules have a negligible perturbative effect on the 4F energy levels. Ligand vibrations strongly split and fluctuate the energy levels of d orbitals via crystal field splitting. Vibronic coupling. Minimal vibronic coupling. Electronic transitions take place strictly between unperturbed F levels, F to F transitions. Strong vibronic coupling shifts the electronic states dynamically during molecular vibrations. Spectral output. Sharp, needle-like lines, similar to free gas icons. Broad, diffuse absorption bands. Note: F to F transitions are Laporte forbidden. Because the crystal field cannot effectively relax this rule through ligand mixing, lanthanide complexes display low color intensity, low molar absorptivity, where epsilon, alongside their signature sharpness. 4. Separation techniques. Question 4. Describe the ion exchange chromatography method for the separation of lanthanides from a mixture. On what basis does the elution sequence occur? Model answer. Because lanthanides share a uniform +3 oxidation state and nearly identical sizes, fractional crystallization is inefficient. Ion exchange chromatography is the most precise modern method used to separate them. Mechanism. A solution containing M-3+ lanthanide ions is passed through a column packed with a synthetic cation exchange resin containing acidic groups, e.g., SO3H. The M-3+ ions displace the H+ ions and bind to the resin. Elution. An aqueous eluting agent containing a chelating ligand, like ammonium citrate or EDTA, is passed slowly down the column. A competitive equilibrium is established between the resin-bound ions and the eluting complexing agent. Basis of elution sequence. According to lanthanide contraction, hydrated Lu-3+ is smaller in bare ionic radius but holds a tighter, larger hydration sphere, making it hold least tightly to the resin. Crucially, Lu-3+ has the highest charge density, so it forms the most stable complex with the citrate EDTA ligand. Therefore, the heaviest lanthanide, Lu-3+, moves down the column fastest and is eluted first, while the lightest lanthanide, La-3+, forms the weakest complex and is eluted last. 5. Lanthanides versus actinides. Question 5. Compare lanthanides and actinides with respect to a. Variable oxidation states, b. Complex forming tendency. Model answer. Property. Lanthanides, 4F series, actinides, 5F series, a. Oxidation states. Exhibit a dominant, highly stable +3 state. Rare exceptions display +2 or +4, CE, U, YUB. Exhibit a wide array of variable oxidation states, +3, +4, +5, +6, +7. For example, uranium shows +3 up to +6, and neptunium, plutonium reach +7. Reasoning. The energy gap between the 4f, 5d, and 6 orbitals is quite large, limiting the availability of electrons for bonding. The energy gap between the 5f, 6d, and 7's orbitals is very narrow, allowing electrons across all three subshells to participate in bonding. b. Complex dipole or electrostatic means with hard oxygen donor ligands systems. Reasoning. The 4 to form covalent links. The 5f orbitals extend further out spatially, allowing greater orbital overlap with ligands and imparting covalent character.